Electrostatics, capacitor examples. In this video, we're going to work through 5 different examples. The first one is a classic analysis of the parallel plate capacitor. We'll then use those results to do an example to try to illustrate how big the unit of a farad is. And it turns out a 1 farad capacitor is huge. After that, we're going to analyze the capacitance of a coaxial transmission line. We're jumping ahead in topics, but what's neat about this is at the end of magnetostatics, we'll analyze the same structure for its inductance, and then we can combine our derivation of inductance and capacitance and calculate the impedance of that transmission line. That's not something we've talked about yet, but that will be covered when we get to transmission lines. We'll use that result to then look at an RG59 coax. And so before high definition television, when you twist this little coax into the back of your television, that was an RG59. Then in the end, we'll look at a capacitor with an inhomogeneous dielectric and look at how to handle that. So let's dive right into this. The parallel plate capacitor. This starts off with a device very much like when we're analyzing resistors. We have a dielectric medium here, so it is insulating. That's one difference. And we're characterizing it by its permittivity. So it'll have a conductive plate on the top and the bottom. The separation between the plates is D, which places the bottom plate at Z equals 0 and the top plate at Z equals D. We'll analyze this using the recipe we discussed in our theory lecture. And step 1 from that was choose a coordinate system. Well, this device looks blocky, and so we're choosing the Cartesian coordinate system. The next step is we're just going to let the plates carry a charge Q. So the top plate carries a positive Q charge, and the bottom plate will carry a negative Q charge. That was pretty easy. Now we want to calculate the electric flux using Gauss's law. Now our job becomes a lot simpler if we can borrow from previous lectures when we talked about fields around charge distributions. So remember what the field looks like around an infinite plate. So it didn't decay with distance, and it was perpendicular to the surface charge, and the magnitude was the surface charge density over 2. So if we look at the top plate, which has a positive charge, this conclusion means the electric flux points away from the top plate in both directions. If we apply this concept to the bottom plate, which is now carrying a negative charge, we have a field on both sides of that plate, but it's pointing toward the bottom plate. Well, in fact, we're interested in the medium between the plates. And in this case, the field is double because there's flux due to the top plate and flux due to the bottom plate. So overall, the field between the plates is rho s, and it's in the z direction, not rho s over 2, because we have a q charge on both plates, and we essentially have twice the field in the area between the plates. So what is the surface charge density? All we know at this point is that it carries charge Q. Well, if the plate has area S, then Q distributed over that area is the charge density. So Q divided by S is that charge density. That lets us write our D field, which was just rho S times AZ, is now Q over the area S. Now since we know the electric flux density, now we can calculate the electric field intensity E. And we do that just using the constitutive relation. So the electric field E is the flux divided by permittivity. And that brings us to Q over epsilon, also over S, and it's in the Z direction. Notice the electric field is pointing downward from the top plate to the bottom plate. Now we want to calculate the voltage between the plates. We assumed a charge, we calculated the field, that means there has to be a potential difference. Let's calculate this. We'll calculate that with a line integral of the electric field. So we'll integrate from the bottom plate to the top plate, and that will give us the voltage between the plates. So our integral will go from 0 to D in the Z direction, and we have an expression for our electric field between the plates. It's in the Z direction, and our differential length is dz in the Z direction. The dot product between the two, they're both in the Z direction, so the AZ's disappear. We just end up with this term, Q over epsilon S times dz. However, the Q over epsilon S are all constants and can also come to the outside of the integral. So we bring them outside, and now we just have an integral from 0 to D. So this whole integral here will just be D. And now we have the potential difference between the plates. We're finally ready to calculate capacitance. Remember what capacitance was? The charge Q divided by the voltage. So we know what Q is. That was the assumed thing. We assumed Q on each plate, and we derived an expression for the voltage between the plates due to that charge. And we have this magnitude operation happening here, so we'll just ignore the negative sign, and we end up with Q all divided by the QD over epsilon S, and the Q's cancel. The epsilon S comes to the numerator, and we end up with epsilon times the area S divided by the separation D. And in fact, that is our final answer for the capacitance of the parallel plate capacitor. We do a final check. The capacitance should not depend on the charge Q that we assumed or the voltage between the plates. Another way we could do this is apply a voltage and calculate Q. But either way, the voltage and Q should not be part of our equation for capacitance, and it is not there, so we're good. If somehow there's a Q or V naught in our formula for C, well, there's a flag that we've done something wrong. Next example, how big is a farad? So let's design a capacitor that's roughly the size of a classroom. So let's say it's 10 meters by 20 meters. And let's let the gap between those plates be 1 millimeter. Physically, that's a very large capacitor. There's a lot of area there. What value of capacitance would we get from this? Well, we apply the equation for our parallel plate capacitor, and let's figure it out. We'll decompose our permittivity into the free space permittivity times the relative permittivity. Since this is in air, the relative permittivity will just be 1. And then the area will be length times width. That's our 10 meters by 20 meters. And the separation is 1 millimeter. So we plug in our numbers, and we get an answer of about 1.8 times 10 to the minus 6. So 1.8 microfarads is the answer. So the microfarad, 10 to the minus 6, for a capacitor that is physically huge, that really means the farad as a unit is a very, very large unit. Imagine how big that capacitor would be to actually be 1 farad. It would be 6 orders of magnitude larger than 10 by 20 meters. That'd be crazy. So the conclusion from all this is the farad is a huge unit, and typically we're in the micro to picofarad sort of range when we're dealing with circuit components. Now in modern days we have supercapacitors and ultracapacitors that can get us some very, very high values of capacitance, but those are atypical capacitors, I would say. Example 3, the coaxial capacitor. So on the right, we're showing a typical coaxial transmission line. It has a center conductor of radius A, an outer conductor where the inner radius is B, and some kind of dielectric fill with some sort of permittivity. And we're also giving it a length L. So step 1, according to our recipe, is choose a coordinate system. Well, in this case, our device looks like a cylinder, so it makes sense that we would analyze this using cylindrical coordinates. So that's really the answer to step 1. Step 2, we're going to let the plates carry charges positive Q and minus Q. We'll choose to distribute the positive charge around the inner conductor and then the negative charge around the outer conductor. Overall, the total charge on the inner conductor is the same as the total charge on the outer conductor, just opposite sign. Now we want to determine the electric flux, and we can do this using Gauss's law and some common sense about symmetry. We need to define a Gaussian surface that will integrate the flux. So showing here in this blue cylinder, this will be our Gaussian surface. We'll integrate around this to relate D to the charge to get an expression for it. However, we have metals. And remember from our discussion in boundary conditions, the electric field immediately at the interface of the metal has to be normal. There cannot be a tangential component. So that means if we have an electric field line extending from the inner conductor to the outer conductor, it has to be normal to the inner conductor, normal to the outer conductor, and wouldn't it be kind of strange if it bent and twisted along the way? It doesn't do that. So really we're talking about a field that's forming straight lines from the inner to the outer conductor. So just from the symmetry and the geometry, we already know the basic configuration that the electric flux will take inside of this device. So that means the D field, the flux, will be in the rho direction. And so we could write our D field this way. The only thing we have to do is determine what is D rho. We know it's in the rho direction and it does not have components in any other direction. So let's apply Gauss's law to figure out what the rho component of D is. So we have our equation to integrate flux. We're in cylindrical coordinates. So we have our D field, and we're doing a dot product with ds, and in this case, that is our ds. And we're choosing our limits of integration. So for phi, we're integrating from 0 to 2 pi, and for z, we're integrating from 0 to L. Now, since our D field only has a rho component, essentially this phi expression and z expression just disappear, and we're really just retaining this expression. And then we end up with a D rho times this differential area. So our flux integration is a lot simpler now. So the D rho and the rho are constants. They are not functions of L or phi. They can come to the outside of the integral. The other thing we can do is isolate the phi integral. And so the integral of 0 to 2 pi d phi, what's in parentheses here is just 2 pi. So we perform that integral, we get 2 pi, and now the 2 pi is a constant, we can move to the outside. We're left with just an integral from 0 to L of dz. It's essentially the same as the integral up here, but this will become L. So now we have 2 pi d rho rho L. That expression is the total charge. We can now solve this for d rho. And that's what we do on this slide. So we then have an expression for the rho component of the electric flux. And we can write it as a vector. We give it a direction in the rho direction. On step 4, we need to calculate the electric field intensity. Well, we've really already done the hard work. We just divide the electric flux by the permittivity, and we have our expression for the electric field intensity. So divide by epsilon, and we have our expression. So what's next? Well, we know the electric field intensity now. It looks the same as the flux, just scaled by the permittivity, but it's still in the rho direction. Now we want to know the voltage between the plates, and we determine this with our line integral of E dot dl. So we'll integrate from the center conductor to the outer conductor. So we'll plug in our expression for E, And our differential length when we're integrating from the inner conductor to the outer conductor is just in the rho direction. So we have a rho dot a rho. So the unit vector rhos disappear. We just end up with this expression for the magnitude of the electric field times d rho. We take our constants, Q, 2 pi epsilon, and L, and we move those to the outside of the integral. We have to keep the 1 over rho inside the integral. But now we have something relatively easy that we can integrate. So the antiderivative of 1 over rho is the natural log of rho. Then of course we evaluate that at B and then subtract it, evaluate it at A. Here's our expression from the previous slide. We then evaluate our natural log of rho at B minus natural log of A. We have a negative sign out here that we can absorb into the parenthesis, and we just switch that. And the natural log of A minus the natural log of B is simply the natural log of A divided by B. And that's our final expression for the potential difference between the plates. Now we're ready to calculate capacitance. We started with an assumed charge. We went through a bunch of stuff and got the voltage between the plates. And now we can divide the two to get capacitance. So we have our assumed charge, we have the voltage between the plates that we derived, and we see that the Q's cancel. That's very good. And we end up here. Now we want to do the self-check. Is voltage in this equation? No. Is charge in that equation? No. So that's a good sign that we have a correct equation. And it turns out that is the correct equation for the capacitance of this coaxial transmission line. Now, usually when we specify the capacitance of a transmission line, we don't know how long the transmission line is. So we would like some kind of metric that is independent of the actual length. And so what we can do is specify what's called the distributed capacitance. And this tells you the capacitance per unit length. And so that's real easy. There was an L up here, the length. We bring the L over here, so we have capacitance per unit length, and that is what this expression calculates. So given the distributed capacitance, we can calculate the capacitance of any length coax line. And this is the more meaningful metric. Our next example will build on the last, and we'll analyze an actual RG59 coax and see how close we get to the specified parameters for the line. So a standard RG59 coax, poking around online, the inner conductor is a 20 Aug wire, which means it has about a 0.81 millimeter diameter. The outer conductor diameter is about 3.66 millimeters. The dielectric between the inner and outer conductor is Teflon. It has a dielectric constant of around 2.1. That's pretty low. The specified distributed capacitance for this line is around 87 picofarads per meter. Let's see how close our analysis gets to this. So this is our equation for the distributed capacitance. We plug in our numbers. The relative permittivity, or the dielectric constant, is 2.1. Our free space permittivity, 8.854 times 10 to the minus 12. And then natural log A over B. So our A is 3.66 millimeters divided by 0.811 millimeters. Now here's a trick. We're dividing A by B. So as long as A and B have the same units, it actually does not matter what units they are. So there's no need to convert everything to meters or something. Just make sure they have the same unit, and when we divide them, the units disappear. So we run the numbers, and we get 77 picofarads per meter. So the actual specified distributed capacitance is 87, and we got 77. So we're off a little bit. Our last example is an inhomogeneous capacitor. So here we're looking at the parallel plate capacitor. However, now we have an inhomogeneous fill. And we're going to handle this exactly how we handled the inhomogeneous fill for the resistor. So what we'll do is explode that and treat each homogeneous region as if it were its own capacitor. And in fact, it is. So what we'll do is we'll use our equation for the capacitance of a parallel plate capacitor, and we'll apply this to each one individually, and then we'll use our circuit theory to calculate an overall equivalent capacitance. So for the first capacitor, epsilon S over D, however, S is T times W1. Move on to the second capacitor, epsilon 2 times area 2 divided by D1. And that area 2, or S2, is T times W2. And our third capacitor, epsilon 3 times area 3 over D2. And what is that area 3? It's T times the sum of the two W's, because this is the total width. So those are our three capacitors individually. Now we'll apply circuit theory to combine them. Here's our circuit, and now we can clearly see that we have a parallel combination of the first two capacitors and then in series with the third capacitor. So we combine our capacitors this way to get the overall equivalent capacitance. We have our expressions for the first two capacitors and then our expression for the third capacitor. And if we turn our number crank, this is the expression that I get, and I think that is the simplest expression for the equivalent capacitance for this case.